Welcome to the presentation session for the Digital Signal Processing course. Today, I'm going to talk about Viterbi, which is a revolutionary tool for symbol detection with deep learning. I'm going to start with defining the problem. We'll discuss methodology in detail and float into the key findings and results of the work. We'll also talk about the limitation and conclude with practical implications. Symbol detection is a core function in digital communication where the receiver identifies the transmitted symbols from the signal it receives. The process involves interpreting modulated signals that carry data which have been affected by noise and other channel impairments during transmission. Our commonly used symbol detection scheme is the Viterbi algorithm, which aims to achieve minimal probability of error in symbol detection under various channel conditions. The Viterbi algorithm relies on channel state information, which requires knowledge of statistical relationship between the channel input and output. However, in some cases, obtaining accurate CSI can be difficult, challenging, or unavailable. To address this limitation, this paper proposes Viterbi, which is a data-driven symbol detector that utilizes deep neural networks to implement the computation of the Viterbi algorithm without requiring CSI. Viterbi demonstrates comparable performance to the optimal CS-based Viterbi algorithm and is robust to model uncertainty. Recent years have seen an increasing interest in using deep learning networks, deep neural networks for receiver design with various applications explored. Beginning with the importance of Viterbi algorithm, played a role as a staple in CSI-based symbol detection, particularly its efficiency in channels with a Markovian structure. Viterbi algorithm strength lies in its ability to minimize error probability when the statistical relationship between input and output is known, which is a common scenario in most practical implications. Explaining that limitation that the Viterbi algorithm requires the receiver to have full channel state information to understand the exact statistical relationship, which can be a challenge in dynamic or complex environments. Transitioning to the advent of machine learning network methodologies, spotlighting deep learning networks as they have independence from underlying stochastic models, allowing them to function effectively even without precise model parameters, which is a significant advantage in real-world applications where channel models are complex or unknown. There are burgeoning interest in leveraging DNNs for receiver design, noting their successful applications in decoding linear codes, aiding in MIMO systems, equalizing multipath channels, and sequence detection using RNNs. In current research landscape, where DNNs have often been applied as black boxes with the hope that sufficient training will enable them to mimic or surpass the performance of dedicated algorithms like the Viterbi. How about considering that how integrating model-based methods with DNN could potentially lead to gain in performance, efficiency, or training efficacy? The innovation here represents a significant leap forward, melding the well-established Viterbi algorithm with the dynamic capabilities of machine learning, particularly deep neural networks. It's a fascinating example of how traditional methods can be enhanced through modern technological approaches. A standout feature of Viterbi is its use of deep unfolding techniques. This is a novel application in the field, marking that first time such techniques have been applied to Viterbi algorithm. During my review, I was completely impressed by the practical advantages of this net offers. Its design is elegantly simple, which facilitates efficient training with very small dataset. This is a crucial attribute considering the rapid evolution and variability of consistent communication environments. Moreover, the ability of Viterbi is maintaining a consistent performance irrespective of fluctuating channel condition is a testament to this robust design. From the empirical evaluation, it's clear that Viterbi not only keeping pace with the traditional CSI dependent Viterbi algorithm under ideal condition, it actually surpasses it when faced with the uncertainty in channel information. Here we come with the methodology part. The first part of the method is the system model, which includes recovering a block of symbols transmitted over a channel with limited memory. It also symbols uniformly distributed over a constellation set independent of time index. The output at each time index described by a stochastic mapping of the past symbols within the channel's memory. The channel is assumed to be stationary, meaning probability distribution function PDF does not depend on the time index. Here is a figure of the system model. The second part is the Viterbi detection algorithm. So optimal decision based on the maximum likelihood decision considering equiprobable constellation points. The decision rule simplifies to minimizing the negative log likelihood optimization of the observed channel outputs. It also utilizes the steps of optimality principle of dynamic programming to solve the optimization problem recursively. It describes the algorithm in the right side describes the steps of Viterbi algorithm as initialization, recursive computation, and output decoding. This is the main part of this contribution of this paper, which is called Viterbi net. Here, understanding the role of channel state information is fundamental in traditional symbol detection methods. In Viterbi algorithm, a cornerstone in the field relies heavily on the CSI to compute the log likelihood function, crucial for determining the probability of error in symbol detection. This step involves analyzing the extent of CSI's role and its implication on the algorithm's performance. Moving forward to the Viterbi algorithm's design requires an assumption about the memory length of the channel. This research step posits that the receiver possesses accurate knowledge on a reliable estimate, which is critical for the Viterbi algorithm's operation and less stringent than having complete CSI. The channel's stationary nature implies that the log likelihood function is invariant to the time index and solely dependent on current and past symbols up to memory limit. This step involves leveraging the property to reduce the complexity of the algorithm, ensuring the same function is used across different time indices. To bypass the explicit computation of the cost function using CSI, the phase of research entails designing an ML system capable of learning to approximate CIS from the given data. The system is trained to predict the cost function, effectively replacing the need for CSI in computation process. A significant challenge arises from the fact that standard DNNs output the conditional probability of the symbols given the channel output, which is the inverse of that the Viterbi algorithm requires. The step is focused on developing strategies to correct this inversion, aligning the DNN's output with the algorithm needs. To convert the DNN's output to a format suitable for the Viterbi algorithm, Bayes' theorem is applied. This step mathematically transforms the DNN's output to the required conditional PDF of the channel output, given the transmitted symbol. An LSTM network with a softmax output layer is employed for its efficacy in sequence classification tasks. The step of kernel density focuses on estimating the marginal PDF of the channel output, which is a non-parametric way of modeling the probability distribution. Finally, developing a mixture model for the channel output distribution to approximate the marginal PDF. Here is a proposed Viterbi decoder figure for the Viterbi net. Let's talk about the result of this approach. The first and foremost point for this approach was the data-driven term, which learns log likelihood function without needing full CSI. Also, when adequately trained, Viterbi is expected to approach the performance of the traditional CSI-based Viterbi algorithm. This is a significant achievement, demonstrating the potential of ML in reaching benchmarks set by established methods. Utilization of Markovian structure. Viterbi is tailored to reverse the Markovian nature of finite memory channels by computing log likelihoods. The design is relatively straightforward and simple in design. The training efficiency is quite good in terms of smaller set of training sample, highlighting in efficiency and quick adaptability. Also, the potential for runtime adoption can vary depending on the training dataset, but it can adapt to channel variations potentially using pilot sequences. Like the conventional CSI models, based models, complexity increases for Viterbi net when the larger constellation size and memory size and channel memory. It also has scopes for complexity reduction inspired by method like beam search. Adaptability to scenarios with unknown channel models is the most important practical implication of this work. It is also efficient and reliable symbol detection despite channel model uncertainty, and it approaches performance of optimal CS-based Viterbi algorithm. In conclusion, Viterbi as a machine learning adoption of the Viterbi algorithm by reimagining the Viterbi algorithm through a machine learning lens. It has a focus on log likelihood computation without the full information of CSI that typically requires CSI to calculate the log likelihood computation. It has a hybrid architecture of combining ML processing with traditional model-based Viterbi detection. The training efficiency and the reliability in CSI uncertainty makes this project and this work quite capable and quite practically implementable. Thank you very much for your time.